So, as you can see, the title is a little bit different than in the program. It says Part 1. So the first thing about first parts of anything, you should never call something Part 1 because usually you are not going to have the Part 2. So this is a risk that I decided to take. The reason is that the topics that I wanted to talk about kind of got a little bit bigger than I expected, so I had to split the presentation into 2 sections. And this is the first one. Okay, so a little about me, although I guess we already know each other from previous C++ rushes. I'm, as people are usually on the stage, independent trainer / consultant. I'm also a KDE developer. I kind of wrote a book, and I teach at the university. And for people who know me, I changed this slide. I now included a photograph of Philip Wadler, aka the Lambda Man. And this is my favorite quote by the guy called, "Make your code readable. Pretend the next person who looks at your code is a psychopath and they know where you live." And as usual, this doesn't mean that you should write everything with go-tos, for loops, etc., because you want people to understand what you write. You want to write beautiful code. If somebody needs to learn more C++ in order to understand your code, that's perfectly fine. So we're going to start with a story about some different area of programming that's not usually connected to C++. So in our world, we usually have some state, and then we have getters and setters to be able to change the state. Now we've learned that mutable state is bad, etc., and that's one of the reasons why functional programming started getting traction. Because in multi-threaded environment, it's not really a good idea to have a shared mutable state. So in functional programming, instead of mutating the current world, you're always creating new worlds, just a little bit different. So clone the current world with some action performed, clone it again, and then you get a lot of worlds. Now, obviously, this would be really inefficient. If you want to know how this can be efficient, you can visit the talk by Juanpe tomorrow on postmodern data structures. Usually, we are just interested in the last world that we created. For example, if somebody still is looking at one of the old worlds, it's fine. But usually, when we want to change the world, we want to live in the changed world and not have a copy somewhere else. So the same guy, the Lambda Man, wrote a really nice paper about a thing that he called linear types. The idea of a linear type is if you have a value of set type, you can use it exactly once. And if you can use something exactly once, you don't need garbage collection, you don't need reference counting. And the best part of the article is actually the title of the article, "Linear Types Can Change the World." Because, as I said, in functional programming, in pure programming, you can't change anything. You just create new worlds. And this thing allows you to, even in functional programming, to change the world. So now you're probably wondering, okay, this is a C++ conference. And I'm talking about functional programming purity and all the foreign things that we've never seen in C++. But in C++, we have some other problems that can be solved in a similar way. So everybody knows that this is the single most important character in C++. The reason any resource that you acquire, this curly brace automatically releases it. So any resource is going to be freed. Any counterpoints to this claim? Can you think of a resource that you can never get back? Okay, somebody said pointer. I wanted something a little bit more abstract. Time. In essence, if you spend time, the curly brace is not going to help you. And usually, obviously, we can write awful algorithms and lose time, but then it's our fault. But usually in C++, we kind of have the problem of losing time by making copies. So before C++ 11, the way we passed an object to somebody else was, okay, let's clone it, which is even worse than in functional languages, as you'll see at Juanpe's talk tomorrow. And then destroy the original because we don't need it anymore. We want to pass the object to somebody else. So enter the most important pair of characters in C++. The pair that allows us to say, okay, this is a reference to something that already exists, but you can do whatever you want with it. So when we want to pass an object from one place to another, we don't need to copy. We can just steal the data from the original object and pretend, well, this is a copy. Because the ampersands told us that the original object is not used by anyone anymore. So moves are quite nice. Now, I guess that everybody knows what move semantics are, but I'm going to talk about them anyhow. If you see the ampersand anywhere, just be happy. Why should you be happy? Because somebody is giving you a present which you can destroy, you can use, you can do whatever you want with it. So this is the normal syntax. Now, it's not to be confused with trefref. If you have a template function and you call a trefref, it's obviously not move. It's meant for forwarding. It can accept anything, right? So how can we restrict a template function to accept only movable values? So before C++ 20, template metaprogramming was strictly a duck-typed language. You can think of dynamic typing from Python or something else. With C++ 20, we got a new beautiful feature called concepts that allows us to create restrictions in the duck typing, which kind of makes it a type-safe language a little bit more than it used to be before. So what are concepts? Just let's say we are in pre-C++ 20 world, because it's still not 2020, and you have a meta function that returns a bool. So you have a const expr bool called isInt, and it checks whether provided type is the same as int. Completely useless function, but bear with me. In C++ 20, we got a new keyword that's called concept. And whenever you see concept, think of const expr bool with some fancier syntax. Now, a really important note, never in your life create a concept that is called isInt. So if anybody from the committee who works on concepts sees this slide, just note that there is a huge note below, this is not a proper concept. Concepts should model something more abstract than just check whether something is an int or something similar. So now we can create a function, a generic function, that works only on ints. Really cool, right? So we are creating a template function, so we are generic, but let's restrict it and make it work only on ints. Obviously, this is useless, but this demonstrates the syntax for using concepts. So you can write template type name t, and then put some restriction on the type t. We could have used also the original const expr bool function here. So with the requires syntax, we are not obligated to use only concepts. We can use any compile time const expr bool value. So the question is, what should I do? I want to create a function that accepts trefref, but it doesn't want to accept anything that is not a R-value reference. We can consult the reference collapsing rules, and then we can notice that any time that we have an L-value reference, after collapsing, it's still going to be an L-value. And we want to allow only R values. So if we want to restrict our function, we can just say okay, it's a generic function, but we require t not to be a L-value reference. And now we have created something that was not really possible in C++11, at least not easily. We have created a generic function which cannot be used to copy values. It always accepts only R values. And a special kind of function, member functions, if you want to declare that the instance of your type needs to be an R value in order for a member function to be invoked, then just a reference qualify it with ref. And then the reference to this is going to be a temporary. Okay, so let's see an example of when copies can be problematic. So we have something called eStream sequence. We all wrote something like this in our lives. In essence, a wrapper around iterators for input streams. And we have a string result, and we are concatenating everything that we read from the standard input onto that string. But obviously, you submit this to Sean parent, and he rejects your code because it's a raw for loop, and we should use algorithms, etc., etc. So let's switch this to an algorithm. And just imagine that I use the full syntax of std accumulate. So what's the problem here? The problem is that accumulate used to be implemented in this way. Again, I say used to. In current standard, it is still implemented in this way. So whenever we write init plus dereferenced first, it's going to create a new string. It's going to assign that string to init, and etc., etc. So for each of the plus operations, we are going to get a temporary string, and then it will be destroyed before we exit the function. In C++20, the algorithm now looks like this. So instead of saying init is something that we want to copy, here we say, okay, after this point, the current value of init will never be used. So you can abuse it as much as you want. And if you have std move of a string plus something, it will be equivalent to calling the .append. It's internally implemented by calling .append on the already existing string. So this is going to be much, much more performant than the original version. So you should always think that if you copy too much, it's going to kill your performance. So we are going to think of the ways how to avoid copying. So when first I proposed a talk about move-only types, I had quite a few really trollish and negative reactions, like, oh, no, again, or something like that. And that was another reason for me to, let's say, mix this talk a little bit. If you don't want to use move-only types in regular production, they are still useful in some situations. If you're writing generic code and you're writing a function that, from your point of view, should never need to copy something, please write unit tests that work only with move-only types. The second example where move-only types are really useful is when you have ranges, when you have reactive streams or anything else. With reactive streams and ranges, you are passing values from one transformation to another. If you're passing, you just need a move. You don't need a copy anywhere. Also, with compile time type tagging, it's quite useful when you need to change a type of something but not change the contents. Just move the old contents into the new type. So let's try to define something that will look like linear types in C++. What should a linear type allow? It should allow us to move the values. It should allow those moves to be really efficient. And all the copies should be disallowed. Now the question is, how can we check whether moves are efficient or not? Exactly. So there is no way for us to check at compile time whether some implementation is efficient or not. So we could use a really, really bad approach, which kind of works in some cases. We can say moves should never throw. If a move throws, that it means it's kind of a little bit more complicated. So let's assume it's less efficient. If it doesn't throw, let's assume it's kind of, most of the time it's efficient. It's obviously a really bad metric, but we don't have anything better than that. And obviously, as I said, copies should be disallowed. So what does movable mean? If we have a value of type T, we should be able to see it as a value of type T. Kind of no-brainer, right? If we have a string, we can use it as a string. The other part is if we have an R-value reference to a type T, that we still can use it as a T. Why? Because we can just pull the contents of the original T and put it into our T and just use it as if it were a T. So we can define a template meta function called linear usable as, which will tell us, in this case, on the right-hand side, T is usable as T, and trefref is usable as T. Now, questions? Okay. How can we implement linear usable as? A type U is usable as T if T is no-throw constructible from U, if U can be no-throw assigned to a T, and if U is no-throw convertible to T. Fair enough? So it's a little bit more complex. This should be much nicer if this was just one check instead of 3 different ones. Now, how to disallow copies? We want to disallow to see tref as a T, because that would mean copying from the original. We don't want const tref to be a T, and we don't want const T to be a T, because all of these require a copy. Now the question is, can we use the previously defined function usable as? Can we just say, okay, something is non-copyable if it's not usable as, not usable as, not usable as? This is a trick question. And obviously, I made the sentence sound like the answer is yes. The problem is that there is a gray place between black and white. So on one hand side, we have a lot of and. And if you just said no of that, it would mean just one of these. If failed, then it is not copyable. We want to abandon all the ways that a value can be copied. So we can define unusable as, which would be essentially the same as the previous one, just explicitly. It's not constructible and it's not assignable and it's not convertible. In this situation, we don't care about exceptions. We want to forbid any type of copying, regardless of whether an exception can be thrown or not. So that's what I mean about the black and white and everything in the middle. Okay? So we can define a concept called linear, and we can say it's no-throw destructible like any sane type is, and just copy that T can be used as T, tref as T, and that we cannot use any of the normal references nor const T as a value of type T. So if we have a beautiful generic code, we create 2 variables for which the type is deduced automatically by the compiler. And we want to restrict these types to just be linear types, we can replace auto with linear. Now, the important thing to note, this is again a concepts feature, this is still automatically deduced type. It's just that after the type is deduced, the concept is going to be checked, and if the concept fails, you'll get an error. So this is almost the same as if you wrote auto, but with the context per bool being evaluated, and if the context per bool, well, static assert. Just imagine auto with a static assert. So in this case, make unique is a linear type because it is movable, it's not copyable. And the strings, the built-in std string, is obviously not a linear type because it allows both moving, but it also allows copying. And we said copying is bad for performance reasons. So if we wanted to write our own accumulate, and we want to force the accumulate not to ever copy anything, we can just restrict that, that the type name t needs to be linear. Again, maybe this is not really useful for production code, but for testing and putting restrictions on on functions, I would say always put as many restrictions as you want until you realize that you actually need to break them. It's like const by default, and then change it to non-const if you really need to change the value. So this is the basic syntax for defining restrictions on certain types. So you say template type name t as usual, and then say requires and put some constraints on the type t. Now, if the constraints are as simple as this, you don't even need to use the requires keyword. You can just say template linear t. It's equivalent as the previous one. So the t will be deduced, and linear will create a restriction on the type. Now, in this case, it's still a little bit more complex than it needs to be. If we can use auto axis, which means that the argument of a function will be automatically deduced, which means that the function is already a template regardless of linear t, maybe it would be useful to have the possibility to also define the second argument not with a template type name, but something regarding auto. So one of the proposals, I think the original proposal for more simpler syntax for using concepts in functions, proposed that we could just say, instead of t init, that we could just say linear init. Obviously, the problem that people had with the proposal is that then you need to know whether the linear is a type or a concept. If it's a type, it's a normal function. If it's a concept, it's a template function, and it needs to go in the header. So the solution to this problem was to use both the name of the concept and the keyword auto. Because again, auto communicates that it's going to be a generic function, it's going to be a template regardless of the missing template keyword. So if you want to create as short function header as possible, you can use auto for non-restricted types and concept auto for types that you want to restrict. Any questions so far? Okay, so the question is why it's not usable in production. If you're writing accumulate, you probably don't want to forbid copyable types. You just want to make sure that your accumulate uses move if it can. So I would say if you're writing something like accumulate, don't restrict the type in advance, just test it with movable types that it does exactly what you want. Okay? I didn't answer, or okay. So, what should we do with non-linear types? If we have std string, obviously we want to use std string in our software. But sometimes we want to restrict the copying. And as usual, we are going to write a wrapper. And this kind of hints how would you implement any kind of movable, linear type in C++. Just in this particular case, we are creating a wrapper on some existing type. So we want to have the copy constructor and copy assignment operator deleted. And we want to have the move assignment and move constructor defaulted, and obviously no except. So this part should be fairly trivial at the moment. As far as the constructor is concerned, we can take an R-value reference of type T. Now, important to note, even if this is tref, this is not a forwarding reference, because the template is not on the constructor, but on the class above it. So this is going to be an R-value reference always. So when we initialize m-value, we are going to move the value from that R-value reference into our wrapper. We can also create an in-place constructor. There are different ways to do this. The simplest way is just to say the first argument is std in place t. And if somebody calls our wrapper with std in place t, comma, some arguments, we are going to call the constructor of the underlined type t and forward those arguments. Now, in this case, these are not R-value references, these are forwarding references, because, again, the template is on the constructor and not on the class. And now the most important function of all, the function to fetch the value from the wrapper. If you want to be a good citizen in the world of linear types, all your member functions should be decorated with ref, which means that any time that somebody wants to use your object, because as we've seen, the rule is the object can be used only once, you need to denote it, okay, after this, consider I've been moved from. In this case, when we create a wrapper, we are stealing the original value and putting it inside of the wrapper. If somebody calls a .get, it's a proper action. It's not a dummy getter. It's an action that pulls the value out of the wrapper. Okay? And we're going to return tref because it's a little bit more performant. And the most important part on this slide is no discard. One of the best features of new C++. If you remember anything from this conference, from this year, or anything else, please remember to put no discard everywhere. If you have a function that returns a value, it probably has a reason to return the value. Don't forget about the value. In this case, the reason is really strong. If you're going to steal the value from somewhere, please don't discard it afterwards. Okay? So that's for get. Obviously, you can create dereferencing operator, etc. I wouldn't advise it because it kind of misses the point. With a function that's called .get, you know what you're doing. You're pulling the value outside. And if you created an operator star, it would look like dereferencing, but again, it would steal the value from inside of the object. Now we can create a user-defined literal that creates linear strings. How do we do it? Just say, OK, operator, quotes, quotes, and const star data and the size. We can just pass it to the in-place constructor of the string and say, OK, just use the data. It will be null terminated, so the constructor should pass without problems. And now we can use the accumulate, our version of accumulate that works only on linear types, by passing, instead of concatenated s, concatenated underscore linear string. So it's not going to pollute your normal code in many places. Now, the big question, when people usually say that moves are useless because we have so many beautiful optimizations inside of C++ compiler. So we have return value optimization, etc., etc. Now let's check whether any of the things that we've seen so far create any overhead. So first we can demonstrate what happens to our really complex linear wrapper. If we have an std string and we are calling .append on it, for some reason I wrote std move before .append, it doesn't make any difference. If we wrap everything inside of a linear wrapper, the assembly code grew exactly 0 lines. So the compilers are nowadays extremely, extremely well behaved as far as wrapper types are concerned.
Can you just create a browser TRFF and you don't need the
Can you repeat?
You can just create a browser RefRef for custom to your value reference, and this case you don't need function get, right?
So the question is, I can just define as type refref. Okay, I don't like that. So the question is, I can create operator trefref instead of using .get.
Yeah, otherwise how you can accumulate on your linear type, right? Inside of this.
Well, you would need to write a lambda that knows how to work with linear types. Now, I do see your point. I'm trying to be a little bit on the more strict side than on the easier to use side. Because one of the things that I really dislike, and we've seen that during Nico's keynote, the fact that we can implicitly convert string to a string view. Anytime that you break the type system and the operator trefref would be kind of a breaking the type system, would produce problems later on. That's why I prefer to explicitly say .get when I want to steal a value from somebody. Otherwise, you would just lose your wallet or, or whatever else, and you will, because it was an implicit conversion, right? So as far as GCC is concerned, this is with 03, I think. Absolutely nothing happens in assembly. But we have a stronger type inside of our program. Now the question is this better than return value optimization? Okay, and I'm hearing some yeses in the audience, pretending that it was yes. Obviously, return value optimization is an amazing optimization. So you'll have a really dummy function which accepts a string, does something with it, and then returns the string. Now the question is this going to be optimized? Well, by the look of the assembly on the right-hand side, this is not going to be optimized. So RVO is amazing, but it doesn't work always. Even guaranteed RVO is amazing, but it doesn't work always. Why doesn't it work in this case? Because the value that we would want to steal from or construct is the argument of the function. And usually when we teach C++, we pretend that it's the same if we create an argument of a value type, or if we catch it by constref or something else and then construct the value type inside of the body of the function. And obviously it's not true. Return value optimization doesn't work in this case because of the calling conventions, etc. So one problem with RVO is that it's not really that reliable. So we can have RVO, In the case of RVO, we are constructing the value directly in the caller. Okay? We can also have a situation that when we call a return something, it's going to use a move constructor in the caller if your compiler implements the resolution for the CVG 1579. Otherwise, you're going to create a copy. So for people who, obviously, normal people don't know what 1579 is, if you have some situations where RVO is not possible, one of those situations is if you are returning a type T and the return type is something else. Nowadays, C++ compilers don't need to call the copy constructor. They can just move the value inside. But as far as this slide is concerned, any of these approaches, even RVO, is going to construct a value. So if you have a slow constructor, it's going to have an impact on your code. The only difference is that it's going to be a normal constructor, and in the second and third place, move and copy constructors. Okay, so we've seen this. And for this reason, there are people who advocate this style of writing code. Instead of using return values, you can use input-output parameters of a function. And obviously, as you can see on the right-hand side, this is much more efficient than the version that used normal syntax. In essence, 20 lines of assembly versus 81 lines of assembly. Here, everything is beautiful, inlined, etc. But the problem is that this is not really a pure way of thinking. It's not a nice way to write your code. It's efficient, but it's not logical. For example, one of the toughest things to teach to most people is std_getLine, because it's accepting a stream and it's accepting a previously created std string to which to store the value in. So what can we do to solve this? We can just say, OK, the input parameter is a ref to a string, and the result of the function is also a ref to a string. It's essentially the same as this code, just with a couple of more refs. But as far as the efficiency is concerned, the only overhead compared to the input-output parameter is the return at the end of the function, because we are returning a value, and in the case of the function that accepted a normal reference to a string, it had no returns. So if you want to create, let's say, a nice and functional API, but you still want to have the same benefits of using input-output references, you can just say my input parameter is a ref, my output parameter is a ref. Now the question is, there are many guidelines in the world that forbid you from returning refs. I think Chromium has one of those. The usual reason for forbidding references is that you can get dangling references, obviously. In functions like this, is this possible? It's not. You're getting a temporary from somewhere else. Somebody else is going to deal with the lifetime of that object. When somebody calls your function, you're returning the same reference with the same lifetime, etc., etc. And when all the functions are called, only then the reference can be destroyed, unless, obviously, its lifetime is prolonged by constref or something like that. And yet again, the difference in the assembly code just by adding a few ampersands to your code. So this is the reason why this is safe, because all temporary objects are destroyed in the last step evaluating an expression, and they're going to be destroyed in the reverse order of their creation. So let's return to our beautiful example with accumulate. The original accumulate in C++ 17. This is the assembly that you're going to get by concatenating strings in a vector. So we have 238 lines. If we use the C++ 20 version, we get to 140 lines. Now, do you all can see the optimization that we can make to this code? The return type of a lambda doesn't need to be a string. Again, it can be a string ref. And we've got down to 57 lines. So don't be afraid of references. I've got a warning with okay. Is it
related to the RAII reference?
I haven't checked, to be honest. And this is not live, this is a screenshot, so I can't, I'm not really in the Godbolt mode at the moment. But that could be a reason. Well, we can check it later. So, how can you improve your programs? Obviously, if you opt into linear types, you're going to be quite restricted. So you're going to you'll need to change the way you think about designing software, etc., which will be in the second part of this talk. But you can get a lot of benefits when performance is concerned. Even if you don't think in a functional way or with linear types way, thinking about all value references and avoiding construction, even if it's a construction by RVO, you can get significant benefits. Now the only problem that you can have with this design is if you make mistakes, which is much easier to do when you have references instead of values. So my advice would be to always use clang tidy to avoid using after move. You should always pass flags to the compiler to make most warnings hard errors. The one that I'm missing here is obviously no discard. If you're using no discard, please tell your compiler to report an error if you're discarding a value. Because as developers, we are usually compiling huge projects which already have hundreds of warnings. If the compiler just gives us a warning about no discard, we are going to discard it. So instead, mark everything as hard errors. Okay, so, and let's say the last thing about error handling. Unless you listen to the talk that will be tomorrow by Phil, you should use std optional, you should use std expected and boost outcome, etc. for error handling. If you use exceptions, they kind of can get in collision with the idea of linear types. Because if you're promised that you're going to use something once and exactly once, what does it mean to throw an exception? Did you use that value or not? So it's much cleaner if you want to obey some rules. It's much cleaner to use optionals, expecteds, etc., than to use normal exceptions. Wrong slide, and this should be the end, 15 minutes to the call. So, thanks. Questions?
Yes, Ivan, thank you. Does anybody have a question?
Thank you for talk. I have a question about when you accumulate in body of accumulate algorithm. when you write move in it, I didn't get how it why it performs better.
Okay. Do you remember the number of the slide? Okay, yeah.
Yeah.
So if you just say init plus dereferenced first, this means init might be used afterwards, so we cannot do anything with it. We should not change it. When we want to plus something, it's going to allocate a new string, copy the data, and then use the new data and assign it to the previous init. So that's the slowness. What is the benefit if you say stud move? If you say stud move, this means that the previous value of the string will never be used after this line. So the operator plus doesn't need to allocate a new string. It can just reuse the same string, which is usually has some, the capacity is larger than size. So often you're going to get away by performing plus without a single new allocation.
Okay, and if I have exactly same capacity, I need to reallocate anyway.
Yes, of course.
Okay.
But again, just imagine, for example, you have a vector of strings that are, let's say, 10 characters, around 10 characters. Because strings grow exponentially, this means that you're going to have to reallocate just as if you used pushback on vector, really, really rarely. And the larger the string, the rarer the reallocations.
Okay, understood. Thanks.
Thank you for the talk. Can you please show the slide with the warning?
Maybe. This one?
Yep, exactly this one. Here you ACC is string ref, so apply stud move on it, and then you have operator plus. So seems like it's operator plus inside stud string, and this operator plus returns string by value. So I have a feeling that you actually create a temporary object here and return a reference to it.
That shouldn't happen. You might be right, but if we call std_move on ACC, which is already an R-value reference, this means that we are just going to call plus on an R-value reference, which should again be just an append.
Well, however, operator plus for stud string returns string by value. So I actually don't see how this, well, I expect it creates a temporary object.
Okay.
You mean content of ACC into this temporary object, which is pretty efficient, but anyway, this is a temporary object to which you return a reference.
Okay, I'll need to check that.
And also pay attention for the warning, probably it's about.
Yeah, it's probably important.
Thanks for the talk. Answering previous question, you can just create overload for ref for string, right? And perform just append and return string ref. And
yeah.
You have no problems. Yes, to what I heard, that Björn Strastrup doesn't like std move, and he thinks that it's some kind of implementation detail, which should be hidden from the user, from the programmer. So I have, I think, 2 questions. What do you think about it? Do you agree? And if yes, can we get rid of std moves, or it's important?
So I would love to see more implicit moves, like the thing with CVG, whatever the number was, 1579. But I don't think that we can get rid of moves altogether. So I think std move. So before the CVG was resolved, you had to use return std move of something, and now it's done automatically. If the compiler was smart enough to do that everywhere, then I would agree that std move is useless.
Okay, thanks.
Hey, thanks for the talk. And for me, it's really exciting that there is the possibility of having mutation with functional syntax. So getting all the benefits of, nice generated assembly, but with a decent syntax. However, I assume this is going to be part 2, but I'm really concerned about the implications of this. So for example, we've seen that if you use something like std string, you would get warnings because you're returning a temporary by reference and stuff like that. So maybe you are onto something. Maybe it's a new paradigm where you recreate the standard library using this kind of ideas, returning arbitrary references, and everything fits well, works properly, and you get very nice assembly with functional patterns. And I'm really excited to see you explore that. But also, I don't know, have you thought about the implications of this? Like, is your guideline to define any function that does a transformation from input to output, taking and returning references? So what's your conclusion? Let's put it this way.
Okay, so as I said, this is a little bit of an experimental talk. So it's to share an idea. I don't want to claim that this is the best idea since sliced bread or anything else. It's a dangerous one. So if you follow this idea, just imagine that you're walking over a minefield or something else. You need to be very careful, which obviously I wasn't. So I would advise investigate this, analyze in your code where can you use it to optimize something if you need to optimize. I wouldn't say use this by default. There is one additional reason why I would never say to use this by default. Sometimes when you are returning a value from a function, sometimes you are returning a transformed input, and sometimes you want to return a proper value. And if you're returning a reference to something, then it will break.
So, does anybody have questions?
Sorry? Okay, cool.
I've got another question regarding the lifetimes about the getters. So if you call such a getter on an object which is already temporary, will that actually work well? Or it can lead to some dangling references?
So regarding temporaries, if you have everything inside of a single expression, then you're going to be fine. The problem is if you try to save a temporary to in a, let's say, some kind of reference, and then use it later, you're going to get undefined behavior just as with any normal dangling references.
But sometimes it's done implicitly, like in range-based for loops or stuff like that, so I think that's a trap that is easy to get into.
I don't see how you can use, if you want to produce an error, you would need to explicitly call the stud move on something that you should not call the stud move on. So I would say that the problem would be in the code where you are assuming that you can move away from, move data from something, and not in the code that uses the ref as the return value. In essence, if you have just a normal function composition, the argument of a function is going to be, well, let's say, result of the first function is going to be a temporary, second function temporary, etc., etc. And the lifetime is going to be quite fine when you access the value when everything is returned. But if you try to save a temporary to something else and then use it later and save it as a ref to something, then you'll get a crash.
Thank you for the talk. Can you can you please open slide with append on the string, and then when you return the string,
Which one?
I don't know. The slide with append, there was
Okay.
2 slides.
This one had append in it.
No, not this one. When you're returning a string and then call append on the returning value, like.
Okay, the one that I said that you don't need to move, right?
Yeah, this
okay.
one, or this one. I think maybe assembly would be better if you then call move on that append, just because I think append does not return a value because there's no overload when with 2 refs, it doesn't have such a...
Fair point. I haven't checked whether append was specialized with ref qualifier
no.
or not. But that's a great comment. Thanks.